What is up, my people? I just want to go over the study guide. So I'm gonna just go through the answers for you all, so that you have this to check over. Uh, and then once I finish this document, I'll post it online too. If you don't want to listen to my voice, I just felt like it might be good for you guys to listen to me explain things and not just write down answers. So, sound waves have areas of high and low pressure called compressions and rarefactions. So there's going to be an area of high pressure where there's a lot of particles in one place. That is a compression. And then there's going to be an area of lower pressure where there's not a lot of air particles in one place, or any sort of whatever the sound wave is moving through. It doesn't have to be air. And that is called a rarefaction. Sound is a longitudinal wave. Meaning its pulses are parallel to its motion, and a mechanical wave, meaning it cannot travel in a vacuum. So sound needs some sort of medium through which to travel. And sound is a longitudinal wave. So if you had a slinky, if you had a slinky, the sound wave would travel like this and not like this, okay? So sound is a longitudinal wave. Sound waves travel faster because the I always say air particles, but because the particles are closer together, sound travels faster in denser media. Because the sound wave can vibrate off the particles more quickly because they're closer together. And then the warmer the temperature, because now I can say air particles because we're talking about the temperature outside. The warmer the temperature, the air particles are moving faster, so the sound wave can vibrate off those air particles faster. So the warmer the temperature, the faster the sound waves travel. When a sound source approaches an observer, the perceived frequency. Now you think about an ambulance, right? As an ambulance approaches an observer, you have that siren, right? Here's your ambulance. That is how you draw an ambulance right there. And then here's an observer. There's a sound wave coming out as you approach. As the ambulance approaches the observer, these sound waves are going to seem closer together because the ambulance is moving in the same direction as the sound waves. So the perceived frequency increases. And then once it passes by, the ambulance is still going this way, and now the sound waves are going to be further away from each other. So the perceived frequency is going to decrease. What is this called? This is called the Doppler effect. Okay? A blank occurs when sound waves bounce off of something and come back to the source. Every one of you has heard this before. It's an echo. If I have a hiker on a cliff, let's say you're at the Grand Canyon, and here's the other side of the canyon, the hiker is going to yell, that sound wave is going to bounce off of this cliff and come back. Okay? And that's what an echo is. When disturbed, all objects vibrate at their own special set of frequency. These are called the object's natural frequencies. Sometimes a nearby object or energy causes an object to vibrate. Okay, so for example, you might have two tuning forks that are very similar in frequency. If I make one of them vibrate and I don't even touch the other, hey,
What's up?
not much. What's going on with you?
Nothing much. Just another day, man.
Well, we start class at 10:30.
Oh, do we?
Yeah.
Oh,
I was
okay.
actually just going through the study guide and recording myself so that you guys can have all the answers to the study guide for your quiz tomorrow.
Oh. You have a quiz?
Yes. Did you not look at your homework / your roadmap?
No. I guess not that far yet.
Yeah, you have an assessment.
Jeez.
It's not going to be worth a ton. But you need to do that study guide, and then you need to make sure you look it over so you know what you're doing.
Okay.
All right. I'll see you in a half hour.
Yeah.
All right, buddy. See ya. Sometimes a nearby object causes. So if I have two tuning forks and one of them is vibrating, and they're pretty similar frequencies, one of them is vibrating, and I don't even touch the other one, the sound waves coming from one of the tuning forks, if let's say this one's the vibrating one, and this one is just doing its own thing, nothing made it vibrate yet. These sound waves are going to cause this tuning fork to vibrate. Okay. So this is called resonance. Okay. And when you talk about the Tacoma Narrows Bridge, right? It was a suspension bridge. And suspension bridges, if you've ever been on one, when you walk on them, they sort of sway, right? Now, what made the Tacoma Narrows Bridge collapse is that the wind was going back and forth, gusting at the same frequency as the natural sway of the Tacoma Narrows Bridge. So it's like a swing. Like when you push a swing at the swing's natural frequency, the swing's going to go higher and higher and higher. For the Tacoma Narrows Bridge, the wind was gusting at the same natural frequency as the bridge swayed. So it was swaying more and more and more until it was too much for the cables of the bridge to handle. So that's why the bridge collapsed. So when the frequency of a vibration that is forced on an object matches the object's natural frequency, I'm sorry. We're going to go back. Okay, sometimes a nearby object or energy causes an object to vibrate, and this is called I didn't do a good job of reading this. This is called a forced vibration. When the frequency of a vibration that is forced on an object matches the object's natural frequency, that's resonance. Okay, and then if I have two tuning forks and they're similar, but they're not the same frequency, they're going to constructively and destructively interfere with each other, and it's going to sound like wah, 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 wah. And that is a beat. A beat occurs when two sounds are similar frequency and interfere constructively and destructively with each other. The range of human hearing is approximately 20 hertz to 20,000 hertz. Dogs and cats have the ability to hear higher frequency waves than the ones humans can hear. These are called ultrasonic. And sound waves with a lower frequency than humans can hear are called infrasonic. Okay, now I just want to go over some of the problem-solving type problems you might see on your quiz. It's a number one says, what is the speed of a sound wave if a hiker yells and hears his echo 2.1 seconds later if the cliff the sound wave bounced off was 340 meters away? So first we're going to write our givens. D equals 340 meters. T equals 2.1 seconds. Okay. Now it's important that you know that if the hiker yells and this distance right here is 340 meters, then the distance for the sound wave to go there and back is 340 times 2, which is 680 meters. Okay, then I can find the speed. Okay, I'm going to say V equals D over T. V equals 680 meters divided by 2.1 seconds. And that's going to give me 680 divided by 2.1 equals 323.8. Must be a very cold day outside. 323.8 meters per second. And then what must be the temperature of the air from problem number one? So this is a great question. So we know that the speed was 323.8 meters per second. Now, the speed at a given temperature is going to equal 331 meters per second plus 0.6 times the temp. Okay? And then to find the temperature, you're gonna plug in your velocity. So 323.8 meters per second is equal to 331 meters per second plus 0.6 times the temp. And then you're going to subtract by 331 on both sides. You're going to get negative 7.2 meters per second is equal to 0.6 times the temp. So you're going to get the temp. I'm going to divide both sides by 0.6. So the temp is equal to negative 12 degrees Celsius. Okay, so that's really cold, but it's like 0 degrees, but it's a cold day out. What do you want me to say? What is the speed of sound in air that is 31 degrees Celsius? So now we're going to use the same equation, except we're going to be finding the velocity given the temperature. So we're using this equation right here, but finding the velocity given the temperature, okay? So V equals question mark. The temperature is equal to 31 degrees Celsius. V is equal to 331 meters per second plus 0.6 times the temp, okay? So I'm going to say V equals 331 meters per second plus 0.6 times 31 degrees Celsius. V is equal to about 350 meters per second, 349.6 meters per second. Okay. What is the beat when a 500 hertz sound is played with a 490 hertz sound? So the beat, these questions are very easy. The beat is just subtraction. The beat is equal to the absolute value of 500 minus 490. So it's 10 hertz. Okay. What other sound would produce a beat of 10 hertz? That would be 500 minus 510 because it's an absolute value. So you would also get 10 hertz here. So there's always two beat frequencies that work. So a hiker shouts and the sound hits a cliff and he hears the echo 2.1 seconds later. If the temperature of the air, so this one has an extra step, if the temperature of the air was 17 degrees Celsius, how far away is the cliff? So we're looking for the distance here. And we don't know the velocity yet, but we do know the temp, so we can find the velocity. The temp is 17 degrees Celsius, and then the time is 2.1 seconds. So the first thing I'm going to do is find the velocity, which will be 331 meters per second plus 0.6 times the temp. And then V is equal to 331 meters per second plus 0.6 times 17, which is going to be 341.2 meters per second. And then you just do, now remember, hiker's on a cliff here, okay? There's another cliff over here. All right, now we know that V equals D over T. We're trying to find how far away the cliff is. How far away is the cliff? Okay, so what we're going to do is when we plug this in here, when we plug V and T into this equation, we're going to be finding how long it takes to go to the cliff and back. Okay, so this is going to be, we're going to say D, if I multiply both sides by T, we're going to say D is equal to V times T, and we're going to get D is equal to 341.2 meters per second times T is 2.1 seconds, and that is equal to 716.5 meters. Okay, that's how long it takes to go there and back. So how far away is the cliff? It's this divided by 2, which is 358, about 358 meters. Okay. Okay, the next problem asks, what is the frequency of a sound wave with a wavelength of 1.2 meters if the air is 25 degrees Celsius? Okay, so again, we're going to find we don't know what the velocity is. We're going to have to find that. The wavelength is 1.2 meters. We're trying to find the frequency. Okay, so the velocity is going to be, again, 331 meters per second plus 0.6 times the temp. And then we do V is equal to 331 plus 0.6 times 25 degrees Celsius. V is equal to calculator button's jammed. Okay, 346 meters per second. And then we can say V equals F times lambda. If I divide both sides by lambda, I'm going to get F is equal to V divided by lambda, which is equal to 346 meters per second divided by lambda is 1.2 meters. So I'm going to get F is equal to 288.3, but I'm just going to round to the nearest whole number. 288 hertz. Frequency is in hertz. Explain how a singer could use resonance to break a glass. So if the singer voice is at the same frequency as the natural frequency of the glass, resonance will occur. And if she sustains this long enough, I don't know why it has to be a she, but if she sustains this long enough, the glass will vibrate violently enough to break. Okay, on a keyboard, you strike middle C, which has a frequency of 256 hertz. Show that the period of one vibration of this tone is 0.00391 seconds. So you're just going to say period equals 1 over the frequency, which is equal to 1 over 256 hertz, which is equal to 0.00391 seconds. Okay, next one. As the sound leaves the instrument at a speed of 340 meters per second, show that its wavelength in air is 1.33 meters. So V equals 340 meters per second. The frequency is 256 hertz. We want to find the wavelength. V, we'll just say V is equal to F times lambda. Divide both sides by F. I get lambda is equal to V divided by F, which is equal to 340 meters per second divided by 1.33, divided by 256 hertz. And lambda is equal to 1.33 meters. Next one, last one. Old Stevie Janowski graphed the speed of sound in different media versus the frequency of those sounds. Show work that shows what the slope of this graph would represent. So speed versus frequency. So V on the y-axis and F on the x-axis. So we know that slope is equal to change in y over change in x, which is equal to, in this case, velocity divided by frequency, which we know from the previous problem, even we know that velocity divided by frequency is wavelength. So that's it. You guys will have an assessment tomorrow. I'm going to post it tonight. You need to do it in one sitting, so all at once, okay? You're going to have an hour to do it. Just do it. Get it done. I prefer you do it just all in one sitting because I think in my chem class, people had some issues with that. Let me know if you have any questions. I will be available all day. If you want to schedule an extra help session with me at some point, I'm happy to do it. Just email me, okay? Like always, email me, and I am around. I have nothing to do, okay? Have a wonderful rest of your day.